Oh, okay.
Okay, thanks, Loiter. Afternoon. Okay, so I'm going to talk about Remote GHCi. The talk is also about stack traces. And I have a little bit of deja vu standing here talking about stack traces because back in 2012 I also gave a talk to the Haskell Implementers Workshop entitled "Why Can't I Get a Stack Trace?" And looking at the state of things 4 years later, it now seems that we have 3 ways. That's got to be a good thing. And maybe you don't all know about these 3 different ways, but you will learn about them in this talk. So during this talk, I'm going to tell you about the always-on stack traces that we now have in GHCi, in GHC 8, and how the process of implementing that solved some other problems at the same time. So, the background for why I started working on this, there's this Haxel project at Facebook, and Haxel is a DSL for writing abuse detection code. We've got a system that's doing lots of abuse detection inside Facebook. It handles 10 to the 6 requests a second. And we have various teams who write code on our platform using the Haxel DSL. And they need to develop and test their code. Right? They've got to write their code. They need to be able to test it against real data and then deploy it. So what we did was we built a customized GHCi and called it Haxel Shell. And it's basically our IDE. This is how our developers develop their code. They load it into our GHCi instance. They test it against live data, so we've actually linked into GHCi a ton of C++ code that can talk to all the back-end databases and so forth. So they can, right inside GHCi, query databases and test their code against the live data. They can also reproduce and debug problems that happened in production. So if we had something that went wrong in production, they can grab the input data, they can load it into GHCi, they can try their code and see what happened and what went wrong. But the problem is that debugging these things can be pretty hard. So for example, if you have some function and you call it on some arguments, it might just say, exception not found. And we have lots of sort of JSON type things in Haxel. So you can very easily get a lookup in a map that the key was missing for. So then what do? Well, you have to go and look at the code for my function, and maybe you look at the different pieces, and maybe you try some simple expressions inside GHCi to see which piece of that function actually threw the exception. And then you have to go and dig some further down and try and find out where it was. And that can be a pretty long process. So what do you want? Of course, you want to have a stack trace of some kind. So we come back to the question, why can't I get a stack trace? Well, there are several answers to this question. The first answer is because you need to use profiling. Right, when you turn on profiling, the compiler keeps track of a stack trace off to the side for you. And that's how we get these nested profiling reports. Another answer is you have to use this new wonderful has call stack feature everywhere. I'll come back to that later. Or you need to use Dwarf. So Dwarf is a new feature for hooking in the code that GHC generates with the system debuggers and generating special annotations that the system debugger can understand. Which isn't actually working yet, unfortunately, but Ben's working on it. It's getting there. So, what I'm going to focus on for this talk is a question. Yes.
Can you speak to the microphone?
Yes. What I'm going to focus on for this talk is the first answer, because you need to use profiling. So how can we get to use profiling in this situation? Well, let me jump to the punchline and show you a demo. So first of all, this is just plain old GHCi. This is without the stuff I'm going to tell you about. Let's load an example program. So my example program is this. So it's a simple program. It has a main function that calls, I've defined map. It's basically just the same as the ordinary map. I've called it my map. And I've got a tail function, which is like the tail function, but it has an assertion in it. And the assertion is that the list is not null. Right, so what happens if we try this program in GHCi today? Well, you get a call stack from the has call stack extension, and it tells you where assert was called from. So that's pretty useful, but it doesn't tell us how we got to that call to assert. So let me just start GHCi again. This time I'm going to say minus prof and a magic flag. And I'm going to load my example again. Oops. And I'm going to say main. And this time, you've got a nice call stack. So this call stack goes all the way from main through the function I called mymap, and then ends up at mytail. And this call stack at the top, we've still got the has call stack. That tells us a little bit more. Well, this location corresponds to the last location of the profile call stack. Alright, so that's one way you can get a call stack. Assert generates a call stack, so let's try something else. Now what happens if I miss out map? So rather than using my local definition of map, I'm just going to use the built-in map. Okay, so I still get a call stack, but this time it's missing map in the middle. And that's because profiling didn't generate cost centers on the built-in map function. Like the same deal as you get with normal profiling. It's annotating all of the code that we loaded into GHCi, but not all the precompiled code.
Oh, but it's better because usually you have to compile all the precompiled code with prop. So
Exactly.
So it's actually better than.
So here's another example. So this is just showing you a different way that you can gain access to the call stack. So this time I've got a locally defined mapm function. It's just the ordinary mapm function. And a local function f. And in f I'm calling this function current call stack. And current call stack is going to grab whatever is the value of the call stack at that point and then print it. Right. So there we got two calls to that function f, and it's printed out the call stack. So I could have done anything with that. And actually, in our Haxel implementation, what we do is grab that call stack and attach it to an exception, and then the exception propagates out, and we can show that to the user. So let me show you. I'll show you a slightly larger example.
Why do you have to say external interpreter?
Because it's not the default at the moment.
But you can't use the internal one
Because I'm going to explain why.
Okay. I'll get paid later.
Yep. Okay, so I'm going to try doing some debugging inside Alex. So Alex is this lexical analyzer generator. And I'm going to start GHCi in Alex using the Cabal REPL with the same options as before, -prof and external interpreter. Okay, so I've loaded Alex, and I can run an example in Alex like this. Okay, that didn't show you anything, but let's do some debugging. So I happened to notice earlier on when I was browsing the code base that we have a trace in here that I could enable, but I have a new kind of trace called trace stat. And now when I run this, it's going to print out stack traces along with my trace. And it's a fully detailed stack trace, goes all the way back to main through all the functions. Okay. So that's the talk.
In call center stacks, don't we squeeze out duplicates? And it looks like there's lots of duplicates.
Well, good question. So they're not actually duplicates. If you look at the source locations on the right, the annotations that we're adding to the code are nested scopes. So the outer ones will be a larger scope, and then it will get smaller and so forth. You could prettify this by removing some of the outer scopes.
But for recursive functions, you will squeeze out the actual.
That's right. Okay, so I'm going to tell you a bit about how we did this. So the profiler keeps a call stack, and we need to somehow get access to the profiler's call stack in GHCi. So one plan is, we could just build GHCi against the profile runtime system. We could just add -prof and we're compiling GHC. and then we can load pre-compiled profile packages into GHCi, and that should be good, right? So that's what I did, first of all. Here's the first commit that I made. And I think I implemented this on the plane to ICFP last year. It's good fun. But we still need access to the stack somehow. So when we're compiling profiled code, there's this option -f prof auto, which you've probably seen, which adds cost center annotations all over your code. And then you get to see them inside the profile or the call stack. But the interpreter inside GHCi, we already add annotations everywhere for doing breakpoints. You may have played with the debugger, or maybe not. It's not all that popular. But we add annotations all over the code already so that you can set breakpoints anywhere you like. So we can just use the same breakpoints for profiling annotations. And inside GHC, there's a common annotations path that adds these annotations, depending on what kind of thing you're doing, whether you're doing profiling or coverage or breakpoints. It's the same path, just with different flags. So I just need to hook it up. So that's what I did, and that's fine. But there's a problem. Profiling is optional for a reason. It's really, really slow. Okay, so this made GHCi, when it's compiling code, when you're loading up code, 2 to 3 times slower than it was previously. And that's because of all the overhead of profiling. Profiling adds extra information to all of the heap objects, and it does extra work when it's calling functions so that it can maintain its call stack. And that's happening inside the compiler, as well as the interpreted code. So that's kind of a lot of wasted effort. And it really matters when you're loading thousands of modules into GHCi, which is what we do at Facebook. So what we really need is a full-speed compiler somehow. And at the same time, we'd like to run the interpreted code under the profiler. So what could we do? Well, here's a cunning idea. One thing we could do is we could have the runtime system load in another instance of the runtime system, because it has a linker. You could just do that, right? Then you could load some libraries and that would just work. And you could have another one. It would be runtime systems all the way down until your head explodes. So that was kind of a cool idea, but then I thought, we still have to communicate between these different runtime systems somehow. So we would need to have some kind of API for communicating, or a pipe, or shared memory, or something like that. And you wouldn't be able to share data between the heaps. They would have to be almost completely separate things, because sharing pointers between these two things would just be impossible. So ultimately, it's going to be simpler just to have separate processes. But let's think about another possibility. What about side by side? And this is a question I've thought about several times. Why can't you just have multiple instances of the runtime system in a single process? Why can't I just call an API in the runtime system that says, create me a new runtime system with a new heap and a new schedule and all that sort of stuff? And in theory, yes, that's quite a cool idea. But it's a really large amount of work. There's a lot of global state in the runtime system. And the killer for this idea is that the compiled code of your program has caps, has static identifiers that point into the heap. And if you had multiple heaps on the go, you would have to have, they would have to go through a table or something. So that makes that idea really difficult to implement. And furthermore, if you wanted to have both a non-profiled and a profiled runtime system, right now that's a compile time option, and we'd have to make that a runtime option. So that's hard. So what we actually do is the separate process idea. So this is the basic picture of the system. We've got GHC running over here in one process. Oh no! Please don't join. I have a PDF if you need.
Were they online? You were live on the network?
Yeah. Yeah, okay, maybe it was a bad idea.
Very trusting man. Just trust him.
Alright, my animation's not going to work. Yeah, okay, so we've got GHC over here, and we have a separate process called the GHC iServe that's going to be our interpreter. And these are running on different runtime systems. GHC is running on the normal runtime system, and the iServe is going to be running on the profile runtime system. And they will communicate with each other by passing messages over a pipe. So how does it work? Well, somehow we have to divide the work of GHCi between these two processes. We have to define an API somewhere, draw a line, and everything that crosses that API will have to be implemented by remote procedure calls. So right now the API contains the runtime linker, because we have to be able to link libraries into our profile runtime system. We have to be able to create bytecode objects, so when GHC has compiled some code, it has some bytecode, it squirts the bytecode over the pipe, and that turns into a bytecode object on the iServe process. We have to be able to evaluate things, and template Haskell is pretty tricky. I won't go into details about how that works, but we have to do template Haskell as well too. So let me just give you a flavour of what the API is across this boundary. There's a type of messages, and messages are a data type, and they have a type parameter. So the type parameter of message is the type that the message is expecting as its result. So for example, to create some bytecode objects, we have a create BCOs constructor, and it takes some byte strings representing the bytecode that we're going to generate, and it returns a list of h-value refs. So these are remote references to objects on the other process. And I'll tell you in a minute a bit more about how that works. And to execute one of these messages, so this is a function that you can call in GHC called iServe command, and it takes the HSCN, that's the big blob of data that you pass around inside GHC, and it takes a message A and it returns an A in the IO monad. So this encapsulates all of the binary serialization and deserialization and returns you the A that you were expecting. So we're right now encoding the message type using the binary library, using generic deriving. So there's a whole module full of deriving blah to make all this serializable. So this is the slide that would have had animations on it. How do we manage pointers from GHC into the heap of the other process? Because GHC is maintaining a big table of the things it knows about and the bytecode objects that correspond to those names and values. And when you recompile something, how do we forget about those references? How does the bytecode objects in the other process get garbage collected? And this is how we do it. We have these things called foreign refs on the GHC side. And a foreign ref is an object that has a finalizer attached to it. So when a GC strikes and it collects the foreign ref on GHC, that sends a message over to the iServe process saying, free this remote reference, and that goes to the stable pointer that's keeping the object alive on the iServe side. That stable pointer disappears, and finally the bytecode object in the other process can get garbage collected. So there's a slightly complicated mechanism underlying all this, but all you have to do is you just manage these foreign refs on the GHC side, and it's fairly straightforward. What about performance? Well, obviously performance is affected a little bit, but it's really not that noticeable. There's a few % difference on the average load command. The serialization format we're using and the library, the binary library, is not very fast, and there are better alternatives, so we can probably improve that by switching to a different library in the future. One tip, if you want a really fast GHCi, is you can start GHCi with -J8 and then a big heap size, and that really speeds things up a lot. So I thoroughly recommend that. Okay, yeah, we're also parallelizing some of the serialization that happens over this pipe, and that helps performance quite a lot.
Simon, when you say sort of load and parsers and type checks and all of that, it's the server thing that's doing all of that and generating bytecodes. That's all happening on the other side.
No.
Oh.
No, GHC is doing the compiling.
Oh, and then it's squirting.
And then sending bytecode over the pipe. Yeah. Yeah, you can imagine drawing that boundary elsewhere. But
it could be a remote guy using all that.
Yeah, but you want the compilation to be fast. That's the whole point. So the compiler runs on the normal runtime system without profiling. So there's some other nice side effects of this, aside from stack traces. And am I out of time?
Well, not time. We have a few minutes for discussion.
Okay. So we used to have this horrible thing with template Haskell, where if you were compiling a template Haskell library or program with profiling, you would have to compile it the normal way first, so that when you were compiling it with profiling, the template Haskell engine would be able to use the first set of objects to run the code at compile time. And now we don't have to do that because we can run the profile template Haskell code directly. There was something similar that happened with dynamically linked object files as well. And I want to mention that some of the idea for this came from GHCJS, which already had an implementation of template Haskell done in a very similar way but using JavaScript. And perhaps if it wasn't for Loite's implementation of this, I might not have believed it was possible. But it's amazingly cunning. And in the future, perhaps we can do template Haskell with cross-compilation by building on this stuff. Okay, and there are things that it could bias later by having multiple GHCi sessions in a single GHC. And running template Haskell without any runtime linking. But these things need some extra work before they can happen. I'm nearly out of time, but I had kind of... Okay, I have a table of comparison between stack trace mechanisms, which I'm going to leave up there, and you can ask me questions about it. Thank you.
Currently, the server and the debug process run on the same machine. Could they run on separate machines and something?
They could definitely, yeah. Right now it's a pipe, so on separate machines it would have to be a socket or something.
Yeah.
The code to handle that is very small and self-contained, so you could certainly do something different.
Okay, and then just a follow-up. If GHC was set up as a cross-compiler, would you then cross-target debug?
Yeah, absolutely. Absolutely.
Really?
Yeah, I'm sure it's not that simple.
Never
But
is.
I think there's nothing fundamentally difficult about it.
We still have a few minutes for questions.
Tell us about stack traces.
Yay! So there are various trade-offs in the different stack trace mechanisms that we have. So you've seen profiling. We also have this Haskell stack mechanism and the dwarf mechanism. So this table here talks about the different kind of properties of these different mechanisms. So one question is, do you have to change your source code in order to use it? So that's true of Haskell stack, but it's not true of the others. Is there a runtime overhead for using this mechanism? And that's very true of the profiling system, but not so true of the others. Do you have to recompile? Yes, when you're profiling, but it doesn't matter so much now that you can do it in GHCi, so that's good. And then there's a question about the accuracy of the stacks. And this is where Dwarf compromises quite a lot, because it's going to show you the actual execution call stack, which will include details of lazy evaluation, things that you probably don't want to see. So the trade-off is that you get lots of stuff for free by sacrificing accuracy in the case of Dwarf.
And it might not even give you the entire depth of the step. It might be truncated as well. Because we don't know how we arrived.
Yeah, tail calls will disappear.
Yeah.
So yeah, I mean, it will show you both too much and not enough. Yes.
Is it lexical only stack?
Yeah. So
It's not real stack trace.
it's a different design choice. So the example here is if you say map of f, do you see map calling f, or do you see the caller calling f? And in the case of Haskell stack, you'll see the caller calling f, whereas in profiling you'll see map calling f.
Last question.
You do, yeah. So you should set profiling on your cabal config or stack config.
Okay, let's thank God.